Hey y'all, today we're going to talk about sampling distribution models and specifically sampling distribution models for proportions. Remember, a proportion is when you have a number of things divided by a total. So if I ask 30 people, do they think homework is important? I can find the proportion of people who said yes. I divide the number of people who said yes by the total number I asked, and I get a proportion. Um, Proportions are things that we look at when we do sampling for categorical data. Um, how many people are in a certain group, and so the proportion of people in certain groups is something that we're interested in. And I want to talk about now if we take a bunch of samples and we find the proportions in all those samples, what it would look like if we put that onto a distribution. What would the shape look like? And then how we can use that to our advantage. So I have this applet here that I did not create, that I borrowed. So we are flipping a coin, and I'll animate. Well, I won't animate. So the probability of getting a heads when I flip a coin is 0.5. I'm going to toss 5 coins, and right now I'm going to repeat this once. So I'm going to get a sample of 5 coins, and we're going to find the proportion of heads. So the number of heads divided by the number of tosses. So I can draw one sample, and you can see I got 4 heads out of 5. And down here I have a XY axis where I have the proportion of heads here, and then the amount of times I get that proportion. So you can see there's one dot because I've done one sample. I've flipped 5 coins once. So let me take another sample. Here I got 3 out of 5. So I could keep putting different samples. Each one of these data points represents the proportion of heads I got out of 5 coin flips. And so I can keep doing 5 coin flips and getting a proportion and putting the point on here. I'm going to do 100 at a time. That's what's nice about this applet. And I can do 100 more and 100 more and 100 more. And hopefully you see what starts to develop. I can no longer see the individual data points because there are so many. I've done 406 samples now. But hopefully what you see is I get this unimodal symmetric distribution, which hopefully you'll remember is what a normal distribution looks like. So whenever I'm looking at a sample proportion and then I get a whole bunch of sample proportions, if I put all those proportions onto a distribution, the more samples I get, the closer that distribution looks to be normal. Sometimes I got all heads, sometimes I got no heads, and a lot of times I got in between. And you could see that the mean is about 0.5, which is what we would expect. We would expect on average to get half heads and half tails. But we know that in life there's variation, so sometimes you get more and sometimes you get less and sometimes you get about average. But when we get a bunch of different samples and we put those proportions onto this distribution, you can see that it becomes approximately normal. And so let me reset it, and I'll do that one more time. Maybe I'll do 10 heads and I'll do it 100 times. So now I'm flipping 10 coins and getting the proportion of heads. I repeated that 100 times and 100 more and 100 more, and you can see that it's not perfect, but it's approximately unimodal and symmetric, and the more I do it, the closer we will get to it being unimodal and symmetric. And that is called a distribution of sample proportions. I'm no longer just putting individual data points. My data points now on my distribution comes from separate samples. So I'm getting samples, finding a proportion, putting it onto the distribution. And I'm doing that a lot of times. So we have had in the past a distribution of individual data points, like we could look at the distribution of height of students in a school, and each data point would be a student's individual height. But now we want to look at data points as a data point from a sample. So each sample becomes a data point now. So as I showed you there on that applet, we can approximate a distribution of sample proportions, anything that we're interested in, again, we can look at um, people who think homework is important. So we could take samples from every high school in America and put the proportion of each sample that said, yes, homework is important. And if we put that onto uh, a distribution, it would be approximately normal. And so when we looked at a normal model, we always wanted to know two things about it. We wanted to know its mean and its standard deviation. And so the mean of our sample distribution of proportions is going to be uh, P, which is the population proportion. We got to be careful here with our letters. P with no hat means population proportion. P with a hat, that is a sample proportion. So much like we had a hat on our prediction equation when we did linear models, because it's an approximation. A sample proportion is an approximation of a true proportion. So we put a hat on it just to say, hey, that's not exactly what it is. And we can find the standard deviation of our distribution of sample proportions by doing P times Q, dividing that by N. Remember, that's the sample size. And then taking the square root of all that. So what we get, and we did this notation before, what we get is a normal model with mean P, standard deviation, the square root of PQ over N. And what's nice about having a normal model is we can find probabilities. We can decide if something is unusual or not. We can determine what's the probability that something happens or doesn't happen. And so we can use this to our advantage. Of course, in order to approximate this using a normal model, we have to meet some conditions and requirements. This is going to be a theme that we carry throughout the rest of the year. Some things need to be true about our samples in order for us to approximate them using a normal model. And the first one is always that we have to acquire our samples through random methods. We have to use some appropriate random sampling method that, like we talked about at the beginning of the year, or else we're going to introduce bias into our data and it's not going to be useful. We need each individual to be independent um, in our samples, and we talked about this before as well. If we can't ensure that things are independent, what we need to make sure is that we sample less than 10% of the population. I can go into that more deeply if you want during class on why the 10%, but what we need is independent individuals in our samples. One person is not affecting the probability of somebody else answering in a certain way or being in a certain group. And then, of course, we need to check that a normal model will work. The way we check that is we find our number of successes. That's what this NP stands for. So when we take our sample, we want to make sure that we have a good amount of successes. So at least 10 successes, at least 10 people that we would consider a success. We talked about this when we wanted to use the normal model to approximate a binomial distribution, a success failure scenario. And NQ was the number of failures, expected number of failures. And this will become clearer when I do an example on what this is and how we get it. It's going to be really important that we establish that we've met these conditions before we do some work and answer a question. And we need to document it and be thorough and explain ourselves. So I'm going to do one example, and then if there's definitely going to be time in class to ask questions, and we can do more together. But take a second and read this, and then I will go through how I'd go about answering this question. So we have some information from everybody's famous favorite CDC that based on previous research, 22% of 18-year-old women have a BMI of 25 or more. And so they took this random sample of female students at a large university and measured their BMI, and 31 of them had a BMI of 25 or more. So we want to know if this is unusual. Usually when we're trying to figure out if something is unusual, we're looking at a normal model. So that we need to establish that we can use that for this sample proportion. So we will document our conditions. It said it was randomly selected. So my 200 female students were randomly selected. At a large college, we can assume that 200 is less than 10% of all female students at this major university. And then we need to calculate NP and NQ, the number of successes and failures. So we have this P of 22%. So we're going to have a normal model where uh, that's our population proportion. This is our standard deviation. So P is 0.22. We can calculate the standard deviation by doing 0.22 times 0.78 over, we have 200 students. So we're going to use this 0.22 to see if out of 200 students we can expect at least 10 successes. So NP is 200 times 0.22, and that is 44. NQ is 200 times 0.78. I did 1 minus 0.22, and that gives us 156. Both of these are greater than or equal to 10, and so that means we can approximate our distribution of sample proportions using a normal model. So we're not going to keep randomly selecting 200 female students and measuring their BMI. We're going to assume that if we kept doing that and we put all of those proportions of female students with a BMI of 25 or greater, that it would be approximately a normal model, and so we can use a normal model to answer this question. So I'm going to draw my normal model. And remember, I'm not very good at it. My mean is 0.22. And I can go out 3 standard deviations in each direction, so I'll do that. And I'm just adding 0.0293 3 times and subtracting it 3 times. And I'll fill that out. So I filled out my standard deviations. And I took a sample of 200 female students, and they found that 31 of them had a BMI of 25 or higher. That's our P hat. This is our one sample proportion, and that's 0.155. And we want to know if this is unusually small. So when we talked about normal models earlier in the year, we said it was unusual if something was greater than or less than 2 standard deviations from the mean. So if something is outside of this boundary, 2 standard deviations above the mean and 2 standard deviations below, then that will be considered unusual. It's not likely to happen. The tails are small. There's not a big probability of that happening. And so our 0.155 is somewhere in here. So our sample is smaller than 2 standard deviations below. It's unlikely to happen. And so this would be considered, yes, we would say this is unusually small. This is an unusually small number of female students on campus with a BMI of 25 or greater. Um, that's just one sample. It's possible to get something that small, but it's unusual. So maybe something about that university uh, or the students who go there that is different than other places. So that's kind of quick to go over this. Of course, practice is required. Questions need to be answered. So if you do have questions, please write them down. This is our first video of the semester, so please bear with me as I get used to making videos again. And please bear with yourself as you get used to watching videos and knowing when you want to ask questions and knowing how you want to process them. Um, as always, please ask me for help, and I look forward to answering your questions.